Welcome back, students. Today we are entering into chapter 5, where the main topic will be entropy. Entropy is a little bit tricky in terms of what it's actually describing. We all have vague kind of ideas in the back of our minds about things like disorder. We'll see what entropy is specifically from a thermodynamics perspective, and entropy comes out of this idea of heat engines. Later in the semester, we'll look at a statistical definition of entropy as formulated by Boltzmann. The topic for today's lecture is going to be specifically on what entropy is and the second law of thermodynamics. To explore these topics, we are going to be looking at a little bit of a strange concept, and that is heat engines. The learning goals for today are going to be to describe a reversible Carnot cycle. And in doing this, we're going to look at entropy is going to come out of this cycle. We're going to want to describe entropy qualitatively and quantitatively, so mathematically be able to just say what entropy is and also kind of say what it is in terms of words. We'll look at the second law of thermodynamics. This is related to our heat engines. We'll talk about that when we get there. And then we're going to, like I said, calculate the entropy for various thermodynamic processes. So we'll go through a bunch of ways of how we can calculate entropy, just like we've seen for things like heat, work, internal energy, and enthalpy. Okay, so the first law of thermodynamics that we've used so far has informed us on how changes occur. We can describe the energy of a system and monitor it as it leaves the system or is added into the system as either heat or work. However, the first law of thermodynamics does not tell us which processes will occur. We can imagine a system that consists of a metal rod. We can then imagine that energy leaves one half of the metal rod and goes into the other half, resulting in one half of the rod being at a greater temperature than the other half. Is this process possible? We know from common experience that substances will not spontaneously change temperature. So if you have a metal rod sitting in your room at home, you're not worried that one half of the rod is going to be very hot and the other half very cold. It's going to be just room temperature. And in fact, if that were the case, so say you had a metal rod and half of it was sticking out into the sunlight and it got hot, that energy transfers throughout the metal rod and it reaches a uniform temperature. That is the direction of natural change. Despite this obvious fact, the above process that we describe, where the rod spontaneously splits into two temperatures, is actually in accord with the first law of thermodynamics. The first law says that energy is conserved, and if energy flows from one side of the rod to the other as heat, that still is abiding by the first law. The first law of thermodynamics cannot tell us if a process will or will not occur. In order to do that, we're going to need to employ the second law of thermodynamics, which we'll talk about today. The second law will allow us to differentiate between natural or spontaneous processes that do occur and unnatural processes or non-spontaneous processes that do not occur. We have to remember that in chemistry, spontaneous doesn't mean necessarily that will occur rapidly, but merely that the process is favorable once any energy barriers are overcome. Now, another interesting thing here is when we're using entropy, when we say something is spontaneous using an entropic definition like we will in the next lecture, we mean that it is natural. And if something is non-spontaneous, that means it is unnatural. So this is a little bit different than chemical reactions where you can have non-spontaneous reactions occur with an input of energy. This is saying some processes physically do not happen. Examples of these would be all of the gas molecules in the room going into one half of the room and leaving the other half vacuum. That is never going to happen. That is an unnatural process that is forbidden when we consider entropy. And we'll understand that a little bit more in the next lecture. To determine which processes are spontaneous, we're going to need a new state function. And that state function, like we've been talking about, is entropy. We'll begin here by talking about the historical definition of entropy, or the thermodynamic definition. And this was proposed by Clausius in 1850 when working with heat engines. And we'll see how that happens today. About 50 years later, Boltzmann proposed a microscopic definition of entropy based on the individual degrees of freedom that molecules have. So we can see this here. Molecules have these individual degrees of freedom that have discrete energy levels. And the entropy, which we denote with the symbol S, we're familiar with this, is a measure of the number of quantum states accessible to a macroscopic system in any given energy. So what Boltzmann's definition of entropy is, and we'll use this more in the future, is that the entropy is equal to Boltzmann's constant times the natural log of W, where W is the weight of a system, which is the number of unique microstates that a system has. With this definition in mind, our familiar concept of entropy as disorder comes into view. A system with only one microstate has an entropy of 0, as the natural log of 1 is 0. As the number of microstates increases, and what I mean by that is that there are more ways of arranging the molecules and energies of the systems, the weight will increase and the entropy will also increase accordingly. We'll look into this statistical definition of entropy later in the semester. For now, we're going to look at the original definition of entropy as it relates to the function of heat engines. What do I mean when I say heat engine? A heat engine is simply a device that converts heat into mechanical work. And so we can see this heat engine here. Here's an example. We have a gas in this piston, and this gas can be brought into contact with a hot thermal reservoir. This will transfer heat to the gas, and the gas will expand isothermally in contact with this hot temperature. As it does that, it's connected to this rotary device here. So as it expands, this device is rotated, harvesting that expansion due to heat transfer as mechanical work. Then it's brought into contact with this cold temperature, it's compressed, and the cycle continues. We can talk about what's going on here in terms of our heat engine with the following. So what we'll note is that heat cannot be converted into work with 100% efficiency. And this is not only practically true, but it's also theoretically true. So in theory, there is no way to convert heat to work with 100% efficiency. And we'll see why that is in the next few minutes. This is an example here of a Carnot cycle. So we're using a Carnot cycle where all of these steps are reversible. We do this because recall that the maximum work we can get out of an expansion is one under reversible conditions. So if we investigate what's the maximum work I can get out of a cycle, we need to be using reversible steps. In reality, we do not use reversible steps, and we get even less than the theoretical maximum that we'll calculate here. So let's follow through and see what's happening in these various steps. If we start at point A, we first bring our gas, our ideal gas, into contact with the hot reservoir. This causes an isothermal expansion by which the pressure decreases and the volume increases at this constant temperature T hot. The piston is then removed from the hot source and it continues expanding. Now as it expands, just like we saw in lab 1, as gases expand, they tend to get cold. So here as it expands, it will reach a colder temperature until it gets to point C, where it has reached temperature T cold. Then it's brought into contact with the cold reservoir and compressed isothermally. So we have an isothermal expansion, an adiabatic expansion, then an isothermal compression to point D, and then it's removed as it's continued to compress afterwards. It increases in temperature up until point A, and we have reached the completion of the cycle. How can we actually describe what's going on here? What is the work that this system accomplishes? We'll go through that in some detail here. We'll go to the board. Before we go to the board, we'll look at what's going on. The total work is, of course, going to be the sum of all of the individual works. So each of these steps has a work associated with it, and the total work that the cycle does is the sum of all of those works. Since we have expansions followed by compressions, it turns out that the work, if we sum up all the works, we actually get the area in between these curves. So the area carved out by these 4 steps is the work that this cycle can actually do. For this reason, I hope you can appreciate that we need to have a mix of isothermal and adiabatic steps. If we only had an isothermal expansion and compression or adiabatic expansion and compression, we wouldn't actually have any net area under the curve. It would just be going back and forth and back and forth. So there would be no work being accomplished. In order to get work, we actually have to have this mixture of steps. So we can calculate the work for this, and we'll go through some examples. It's relatively easy based on the stuff that we've done before. We have 2 isothermal steps, and we have 2 adiabatic steps. So we're going to go through and investigate the heat, work, and change in internal energy of each of these steps. We'll start with the first step. So going from A to B, what can we say about these things? Here we have an isothermal expansion. And so we're going from VA to VB. Remember, all of these are reversible. So we have a reversible isothermal expansion. That means our work is equal to negative nRT times the natural log of V final over V initial, so VB over VA. Since it's isothermal, delta U is equal to 0, since delta U is a function of only T, and delta T is equal to 0. That means that Q is equal to positive work in this case. So Q is equal to nRT natural log of V final over V initial. Note in this case that what we have is a negative work in the first step and a positive heat to go along with that. In the second step, we have an adiabatic expansion. And so the adiabatic expansion has a heat of 0 and therefore a work that's equal to the internal energy. So the work in this step is equal to CV delta T or NCVM delta T. In this case, since our temperature is decreasing, the work is still negative and the internal energy is negative. The other 2 steps are the opposite of this. So in the isothermal compression, we have a negative heat and a positive work and a change in internal energy that's 0. And in the final step, we have a 0 heat again and a positive work and then a change in internal energy that is positive. In total, what do we have? Well, since delta U is a state function, the total delta U of the cycle from A to B to C to D to A necessarily is 0 because we have started at the same point that we ended at. So we have a delta U of 0 because delta U is a state function. Heat and work are not the same, and we'll have to go through some math to show this, but what we can do is show that we have a positive amount of total heat and a negative amount of work, meaning that work has come out of the system and into the environment. So this kind of work can be used to propel our motor vehicles forward and so forth. So let's go into the slides and look at some examples of this. Here I have a table showing the heat and work as well as the change in internal energy for all 4 steps of this Carnot cycle. So we can describe the work by the sum of all of the individual work. So if I call this step 1, 2, 3, and 4, the total work done in this cycle is simply work 1 plus work 2 plus work 3 plus work 4. I can sum up all of these energies and that will give me my total work. Another interesting thing I can show here is that my work is also equal to my heat 1 plus heat 3. Why is this the case? Well, my delta U needs to equal my heat plus the work. Since delta U is equal to 0, since it's a state function, my total work is simply equal to my total heat. And so I should put a negative here to be proper. So it's negative of my heats. So I have this relationship between my heat and my work. What I want to do is describe how efficient this engine is. The engine efficiency is going to say how good is my engine at converting heat into work. So we can say that our engine efficiency is equal to the total work that comes out of the engine divided by the heat that was withdrawn. In this case, it's Q1. Here we see that the total work, the absolute value of the total work, is equal to Q1 plus Q3, and then we divide that by Q1 to get our engine efficiency. We have our heat shown up here in the table. So Q1 is nRT hot, natural log of VB over VA, and Q3 is nRT cold, natural log of VD over VC. And then we'll divide this all by Q1, again, nRT hot, natural log of VB over VA. What we'll do next is use the relationship between temperature and volume for adiabatic expansions. So for reversible adiabatic expansions, the temperature times the volume, so here we have T hot times VB raised to the gamma minus 1, where gamma is the ratio of heat capacities, is equal to TC VC, or T cold the VC to the gamma minus 1. This just comes from our definition of how we find the temperature change for adiabatic reversible expansion. So this is from step B to C, we have this relationship. We also have a similar relationship from D to A, where we have T cold times the volume at the cold temperature raised to the gamma minus 1 is equal to T hot times the volume at the hot temperature, which is TA, to the gamma minus 1. For both of these, we can do a similar thing. So we can simply rearrange this expression and solve for VC. So by dividing both sides of the equation by TC and then taking the gamma minus 1 root, we end up with the following. We have VC is equal to VB times TH over TC, and then to the 1 over gamma minus 1. We can do the same thing over here. So we can say that VD is equal to VA times TH over TC to the 1 over gamma minus 1. In doing so, we can show the following. If we take VD divided by VC, that is simply VD is shown here. So VD is VA times T hot over T cold raised to the 1 to the 1 over gamma minus 1. And then our other expression for VC is VB times TH over TC to the 1 over gamma minus 1. So in doing this, we can then cancel out these nasty temperature-related terms and come up with the following. We can simply say that VD over VC is equal to VA over VB. And therefore, the natural log of VD over VC is equal to the natural log of VA over VB, which is equal to the negative natural log of VB over VA. In doing so, we can plug in this negative natural log of VB over VA for our natural log of VD over VC. So we have the following expression then. Our engine efficiency is equal to NR, and I'll pull out the temperatures here. So we have NR T hot minus T cold times the natural log of VB over VA divided by NR T hot natural log of VB over VA. In this case, we can cancel everything out but the temperatures and find that the engine efficiency is equal to the hot temperature minus the cold temperature divided by the hot temperature. Typical temperatures for these kinds of processes have hot temperatures at 600 Kelvin and cold temperatures at 300 Kelvin. So plugging in these numbers here, we get 600 minus 300 is 300, divided by 600 is 0.5. So they would operate at a maximum efficiency of 50%. The actual efficiency of such engines is around 30% when you account for non-reversible processes. We also notice something that is interesting here, and it probably doesn't seem interesting to you, but we can show this. Here, our engine efficiency was equal to the ratio of heats, but down here, the engine efficiency is also equal to the ratio of temperatures. So we can set these things equal to each other. We can say that Q1 plus Q3 over Q1 is equal to TH minus TC over TH. These two things are both equal to the engine efficiency, so they're both equal to each other. We can rearrange this expression. So I'll multiply both sides by T hot and Q1. Multiplying both sides by T hot will give me Q1 T hot plus Q3 T hot. And then I'll get Q1 T hot minus Q1 T cold. So if I subtract both of these over, what I'll get is I can cancel out this term and end up with Q1 T cold plus Q3 T hot is equal to 0. And what I'll actually do is divide both sides of this expression by T hot times T cold to get it in the following way. I'll say that Q1 over T hot, and I'm doing this because at this first step, the temperature is hot for this first step. That's why I'm doing this extra step here. So I can say Q1 over T hot plus Q3 over T cold is equal to 0. This can actually be generalized to any such heat engine, where the heat of the process divided by the temperature of that isothermal process, and you sum those all up for every step in your cycle equals 0. So in other words, the cyclic integral going from the start to all the way back around to the same point of dq reversible, because I'm having reversible steps here, divided by the temperature is equal to 0. In other words, we have found a new state function. We can define a new state function equal to the q reversible over the temperature. And so we'll define this as ds, where this is the entropy. Here we come across a puzzling result. We have entropy, a state function, that is equal to heat, a path function. How can we reconcile these two ideas? The key to doing so comes in recognizing that the entropy is always equal to the reversible heat. In other words, a specified path. While there can be many heats for a given process, there is only one way that process can occur reversibly. And it's this reversible heat that is related to the entropy. So the reversible heat for a process is not path dependent because the path is specified. If you take a different path, you no longer have that reversible heat. This can be something that is hard to wrap our minds around, that the entropy for a process is equal to the reversible heat, which is usually not the actual heat of the process. So if you have an irreversible process, you have to calculate the reversible heat in order to determine the entropy. Since entropy is a state function, it is dependent only on the initial and final states. And like I've been talking about, for any process, we have to use the reversible heat. When we're trying to calculate the entropy, we simply need to evaluate the integral. So if we have an isothermal process, there is no change in temperature, and so the reversible heat is simply equal to the reversible work. So let's calculate entropy for an isothermal process. If we have isothermal, dq reversible is equal to negative dw reversible, which is positive in this case, nRT over V dV. It's positive because it's the negative work and the work is negative. So our change in entropy is equal to the integral of ds, which is in turn equal to the integral of nRT over V dV. And this is also all over T because our ds is equal to dq reversible over T. So our T's will cancel out, and our entropy is equal to the integral of nR over V dV, which is simply equal to nR natural log of V final over V initial. Remember that this is how we calculate the entropy for any isothermal process, even if it's not reversible. We have to use the reversible work. This shows us that as the volume increases, the entropy increases, which is in our understanding of having more disorder or more microstates possible. We can also calculate entropy for constant volume or pressure processes. So in a constant volume processes, our delta S is equal to, as always, the integral of dq reversible over T. For a constant volume process, the reversible heat is simply QV. So that would be NCVM dt. And now it's, of course, to calculate the entropy, it's NCVM over T dt. So to do this, we would get NCVM natural log of T final over T initial. For a constant pressure process, we'd do the same thing. So here, the integral of our Q reversible would be NCPM, because it's a constant pressure process, dt over T, which would end up being NCPM natural log of T final over T initial. If we want, we can put these two things together to describe entropy change as a function of temperature and pressure for an ideal gas. So if we want to talk about the change in entropy as a function of temperature and volume, we can write that our entropy changes as NCVM natural log of T final over T initial plus NR natural log of V final over V initial. And if we wanted to do pressure and temperature, we could say our change in entropy as a function of temperature and pressure is NCVM natural log of T final minus T initial, and then minus NR natural log of P final over P initial. We could do other combinations as well if we wanted to. Another interesting thing that we will do coming up in the next couple of lectures is want to calculate the entropy for a phase change. So phase changes happen at constant pressure and constant temperature. So think about boiling water. Your water is going from liquid water at 99 degrees Celsius to a gaseous water at 101 degrees Celsius. And so as it's boiling at that 100 degrees, in between those two, it stays at 100 degrees for the entire duration of the boil. The pressure is the constant atmospheric pressure. So we could describe a change in entropy for vaporization for boiling, and this would simply be the constant pressure heat of boiling divided by the temperature at which boiling occurs. So the vaporization temperature. The constant pressure heat is equal to the enthalpy. So the entropy for any phase change process is equal to the enthalpy of that process divided by the temperature at which that process occurs. The same is true for other processes such as fusion or melting. In the next lecture, we will see how we can apply entropy to determine the direction of natural change, or which is we can call spontaneity for a process, which we set up at the beginning of today's lecture. So with that, I look forward to talking about this with you guys more in class.